Hi everyone, my name is Maja Rudolph and I'm a research scientist at the Bosch Center for Artificial Intelligence. Thanks so much to the organizers for having me, for putting this amazing event together, and also for all of you out there who are here to get inspired, hear some other kick-ass women talk about their work. And I'm excited to tell you about my work, which is on multimodal dynamics models for industrial AI. So to set the scene, I will first introduce what I mean by industrial AI. So at Bosch, our goal is to bring AI into all the domains we work in to make better products. We want to bring AI into manufacturing to make manufacturing more efficient. We want to bring AI into engineering so that we can develop new products based on AI or improve existing products in ways that weren't previously possible. And finally, we also want to bring AI into all products. And the crux for industrial AI is that usually the products, they deal with the physical world. It's sensors that sense something about the physical world. Sensors themselves, they have physical rules that guide what and how they sense. The decisions that we want to make, in the end, they do affect the physical world. It's a temperature that might need to be increased in a production plant, or something that needs to be slowed down or stopped, or a decision about moving a robot arm, and so forth. And so really a lot of our work is about bridging the gap between the physical, which is governed by physical rules, and data-driven methods, algorithms, virtual things that I'm sure you're all familiar with. And the way we think about this is through hybrid models. So I'm a data person, I'm a machine learning research scientist. And so I'm sure, like you, I'm used to think in terms of data-driven models, neural networks. I'm sure you all know that they are really great at capturing complex functional relationships. As long as there's lots of data, we can train them. They will capture the underlying statistical rules. And once they're trained, they're actually computationally efficient to just run a forward pass. But obviously there are limitations. So sometimes we don't know how to statistically validate and give guarantees. We don't know how they generalize. In some training paradigms, we need lots of labels, which we might not have. And so this is really where the advantages of the physics-based models come in. So by that, I mean, if, for example, for part of the system, we know what the underlying differential equations are, or if we have a physical simulations for how molecules interact in a certain material, we want to be able to use this know-how together with our data-driven methods. And these physics-based models, and so it depends which ones, but some of them are very data efficient in a sense, so we don't need training data. They also are needed if we want to impose causal constraints on our data-driven models. They're often more explainable. There are strategies to validate some of this, and they are generalizable. So a lot of my work is interacting with domain experts. So at Bosch, there's a really long history of people who have figured out how certain sensors work, need to be built. And there's a lot of engineering know-how. And a lot of my work is about talking to those experts and understanding their language and explaining in our language of data science and of machine learning, how to best get the best of both worlds. And here are 3 results of my work on that. So we've had some ideas on how to make production lines more robust by also using, if you have a huge production floor, there's lots of sensors that are used anyways to control each of the production steps. And since this data is available anyways, we want to use it to get a deeper understanding of what's going on the production line and intervene if necessary. Then Bosch builds these ultrasound sensors. They're almost in every car. So if you drive a car and you park in backwards and it starts beeping, it's probably because one of these sensors recognizes that there's an obstacle. And this is done based on, echo detection, and it works really great. But for physical reasons, there's only a certain range in which it works. And it turns out that based on machine learning, we can increase this range if we learn a generative model of the echo-free oscillation patterns on the membrane. It turns out that then we can actually start sensing in ranges beyond the previously physically possible range. And then another really awesome product is ESP, that is the Electronic Stability Program. It makes sure that when you drive and you start sliding, it recognizes that there's a discrepancy between how you want to steer and what your actually traction is on the ground, and it does a braking maneuver. And so you don't even realize, but this is actually what keeps you stable during driving. And this is also, for many years, it's standard in most cars out there. And here too, we can actually improve the capability by using machine learning. And while those are like very different examples from each other, what they have in common is that usually when we deal with sensors, we have measurements over time. And so what we need is good generative models for these time series data. And I won't go into details here, but in each of these applications, we can use the domain knowledge in different ways to either reduce the complexity of the problem, and thus we need less data, or by making sure that we don't need labels. So from the physical knowledge, for example, in the ultrasound example in the middle, we want to learn a generative model for the echo-free oscillation patterns. And the really cool thing is that if we just have the sensor in normal usage and there is an echo, meaning that there is an obstacle detected, then we know that the oscillation patterns in the beginning are echo-free. And so this somehow gives us our label that something is echo-free, and we can learn a generative model. And then in this near range detection area, we can compare our predictions with actual measurements and thereby find an echo already in the area where the membrane is still vibrating. And previously it was really hard to find the echoes because there's interference in the waves. But with machine learning, it's possible. And so what they have in common is that we need good models for time series data. And this is what I will be talking about for the rest of this talk. And I will focus on one specific aspect of these models. Namely, I will talk about multimodal data. And in machine learning, there's different types of multimodality. So I want to be very clear what I mean by that. So I mean when there's multiple areas in your data distribution that have high mass and other areas that have low mass in between. So here on the right, you can see a unimodal Gaussian bump, or also below that you can see the 2D Gaussian bumps. And on the left, you can see examples of multimodal distributions. Okay, and why is this important? So actually, many data sets that we deal with in the physical world exhibit multimodal dynamics. And I think this taxi data gives a very clear example of that. So here we took a huge data set of taxi trajectories. And to show you what I mean by multimodality, we picked out in the top and bottom 50 routes that have very similar starting behavior. That's marked in blue. And then at the intersection, you can either, for example, turn right or turn left, but you cannot turn straight. And so when you model this kind of data, you want to make sure that, your models are able to deal with it. So a lot of times we use unimodal Gaussian approximations, and this makes it really hard to capture these diverse forecasts, while also being accurate. And this is really important in industrial AI so that we both can, make predictions that cover. So our models need an understanding of many plausible continuations of a trajectory while also being accurate. So we don't want to just average. So the problem is that many models average, and that means that if we have two modes, so two continuations that go in different directions, the average will actually be nonsensical. And specifically, I will be looking at sequential latent variable models. So a latent variable model for time series data means that at each time point t, we have a latent variable zt. And let's say that we observe the beginning trajectories in blue. We want to infer what the latent variables are. And when we want to have learned a model that allows us to propagate the latent variables forward, so predict the future ZTs, and then from them generate our observations XT. And these latent variables, they are abstract, so they are distributions over a d-dimensional vector space, for example, and they should capture certain things like, but they will capture them abstractly. But in this taxi example, for example, things that are relevant to making the predictions, like what's the time of day? Is there a lot of traffic? What is the driver behavior like? And these are things that can be inferred from the beginning, and then it will help the model generate forward. And to be clear, they're not interpretable. It's just numbers that somehow summarize the useful information in the beginning of the trajectory that is relevant for the forecasts. And another thing to note here is that we make no Markovian assumption for the latent variable. Instead, each ZT depends on all the previous time steps. And so this means we will use recurrent architectures, for example, to model the dependencies on the previous time steps. Yeah, and so we developed variational dynamic mixtures. And this is a method for making inference in these kind of sequential latent variable models that is reflecting the underlying multimodality of the data. And this is joint work with my very excellent PhD students, Chen Xu, and Professor Stefan Mann from UC Irvine. And we can, first of all, look how existing methods do on forecasting this taxi data. So all these methods, they're given the blue beginning trajectory and then are asked to make 50 predictions. And we can see that they mostly struggle with this task. So for example, on the right, the recurrent Kalman network, which is a really cool model, by the way. Unfortunately, it doesn't have stochasticity, so it just makes one forecast, which, it goes in the right direction and could be a plausible, but it doesn't reflect the multimodality of the data. Then the variational RNN, it doesn't capture these varying modes. It somehow goes in the general direction and there is some distribution, but you can see that it's not multimodal. It's averaging in some sense. Then the CF-VAE, that's a conditional flow VAE. It's not a sequential latent variable model, it just has one global latent variable. So this global latent variable actually really helps this model to make correct long-term predictions. So it somehow so you can see that it reflects that where the trajectories end up on the far end of the map is also similar to the distribution in the original data. But the way to get there is somehow smoothing out the actual trajectories. And then here you can see the auto-encoding sequential Monte Carlo. I think this does the best job at reflecting the multimodality of the data. You can see these like main traffic arteries, but still there's a lot of unphysical predictions going on. And then this is the results of the variational dynamic mixtures. This is our method. And it reflects this this data much better. So we do somehow see the main arteries as in the predictions. And yeah, and so the rest of the talk, I would like to show you how we got that to work. And to be clear, all these methods, they saw the same kind of training data, which is just a big data set of taxi trajectories. And then here, the examples that I was showing here, these are all test data. Okay, so the variational dynamic mixtures, they are a variational method. And in a variational method, we usually define a model. And then, unfortunately, we can't compute the true posterior. So what we do instead is that we define a variational family here in Q, and which we can take expectations with, for example. And this allows us to fit an objective that gives us the best approximation to the true posterior, namely that is closest in KL divergence between this approximate posterior and the true posterior. And our generative model, I have to speed up a little bit. So I'll just mention briefly that the latent variables, the distributions are Gaussian, and the parameters come from a recurrent architecture that summarizes the past hidden states. And then the emission distribution is Gaussian. And this is actually very similar. So it's a simplification of the generative model that is also used in the variational RNN. And so the question is, how did we get these improvements over the existing methods? And the answer is that this is through tuning the following knobs. So we used a simpler generative model, but we can consider a larger variational family. And this, on the one hand, if we consider a larger variational family, it means that we can reach a posterior approximation that is closer to the true posterior. But actually, we do this in a way such that this Q distributions are explicitly multimodal. And the main idea is as follows. So in our inference model, instead of propagating only one sample through the RNN, we will propagate multiple samples from the previous approximated posterior at ZT-1. We'll propagate multiple samples through the RNN. And this will make sure that we have, instead of getting just one hidden state for the RNN, we actually have a distribution over hidden states of the RNN. And then we can combine each of these samples with evidence. And this gives us a mixture distribution. So our approximate posterior at time t is a mixture that depends both on these samples that were propagated through the RNN and the data. And it's a so-called mixture density network, which is a mixture of Gaussian bumps whose parameters come from a neural network. And this is explicitly multimodal, and is one reason why we, with variational dynamic mixtures, we get this very crisp predictions. Yeah, and so in our paper, we have also an empirical study on more different data sets that are all multimodal, but in different ways. And yeah, we evaluate on many different evaluation criteria, both that look at the accuracy of the predictions, but also on the diversity. So this empirical Wasserstein distance is a new evaluation metric that we propose to make sure that the predictions are also diverse. And on all these evaluation metrics, our method does quite well. So I will refer you to the paper at this point. And thank you so much for your attention. And yeah, I hope you got something out of it. And now it's time for questions. Thank you.